Hello everyone. Today we will go over the analysis involved in the first homework of LRES 510. Today we'll be drawing species accumulation curves based on nested plot data. So today we'll cover basic subsetting using t-apply to calculate means and standard deviations, and basic plotting. So if you'll recall, on day one of the course, we sampled nested frames at Fort Ellis and in Highlight Canyon. In Fort Ellis, we sampled in organic grazed and tilled organic sweet clover and safflower fields. So problem number one deals with calculating and plotting the species accumulation curves and calculating mean species richness in the different shaped frames, sized frames, and among different farm fields. So to get started on the homework, the first thing we're going to do is open R. Here's the GUI window. I had mine already open. I've actually already have the data up, so let's just ignore a bit of that. We'll send that down the way. The first thing you do when you get into R is you should check that you have set your working directory correctly. And so here I know that I've set the working directory correctly, and then I've opened my script, and that script can be found on D2L with the homework assignment and all the needed data text files. So this is what the script looks like. And you'll remember the first day of class we went over a little bit of the features of R. Remember that the pound symbol indicates that it's annotated text and should not be executed as a command. So the first thing we're going to do, step one, is to load the data. And to answer and complete problem one, we'll need the Fort Ellis data. So I'm going to execute the command read.table using the Fort Ellis text file, which is called Fort Ellis data 17.txt. The header is true, and the data object, the data frame, will be called FE when I execute the file. So I'm going to press Apple Enter on a Mac. Remember, it's Apple R on, Control R on a Windows machine. And I'll just switch over to the GUI and I can look to see that the command ran correctly in blue. There were no major errors. So now we can begin to examine the data. The first thing you can do is have a quick look by simply executing the command again. Switching back over, you can see it put up some numbers on the screen and it left it over. I'll slide the GUI window over so everyone can see just a little better. We'll skid it in the corner, and we can see that we executed the command, and if you slide up, you can see that the whole data set is here by species. But really that's hard to look at, and so it's easier quite often just to look at the names. We can look at the names. So we have, these are the names of each of the 25 different columns, 1 through 25. We have type, field, treatment, recorders, area, shape, and richness. We're mostly going to be dealing with the richness variable here. We already calculated richness for you for each of the plots. And so we can then also use head and look and see just at the top few rows of the data set and to get an idea of what it looks like. And so we can see we have type has tilled organic safflower. The field is then a safflower field or a sweet clover field, if you'll remember. And we have tilled organic, grazed organic. The recorders, the area of the frame that we sampled, the shape of that sampling frame, and the richness. So there's some tips to understanding R. First, if you put a $ and a variable, you're calling a specific variable, a specific column. Here we call the treatment column with tilled organic versus grazed organic. We can see that it has the levels grazed organic and tilled organic. If we just like to see those levels by themselves, we can call that up. We can see the we can see that we have two levels, grazed organic and tilled organic. So we can also call up the variable type and the types and levels and shape. So remember that we had grazed organic and tilled organic safflower and sweet clover fields, and we have we sampled in circles, rectangles, and squares. And you'll remember we had a number of different areas of frames, and we can see those. This is stored as a continuous variable right now, so it did not put in levels at the bottom. So remember, we recorded a hundredth of a meter, tenth of a meter, quarter meter, half meter, 1 meter squared, 5 meters squared, and 10 meter squared plots. So the question number 1 is to plot a species accumulation curve. So plot richness on the y-axis and the area of the frame on the x-axis for each of the different types of fields and sizes. So there's a number of ways to go about this. And I'm going through this in a very brute force way, where I'm doing a whole bunch of manual subsetting and collecting of the data, or collating, aggregating of the data. There are much simpler ways to do this, and we'll work on that later in class. By simpler, I mean less syntax, less computer code. But right now I want to go through the ways that we collect it, or the ways that we subset and plot it in a very rudimentary fashion. So the first thing I want to do to solve this problem and plot these different accumulation curves is to do a number of hierarchical subsets. First, I'm going to subset the total FE data set by the different field types. So TO refers to tilled organic sweet clover fields, and we have tilled organic safflower fields. We also have grazed organic sweet clover and grazed organic safflower fields. So we sampled in 4 separate fields. So we do that by just using the command line subset, giving it the whole data frame, and telling it we would just like to have FE type, where that type is only equal to the clover. We gave it this name, FE organic tilled, and SC for sweet clover. We gave it that name. There's nothing special about either of these names. I'm just going to highlight these and execute the commands. Got no errors over here. We look good. Then we can go and subset. Now let's work just with the organic tilled data sets for a second. So we've taken this organic tilled sweet clover down to here. We're going to subset the organic, only the tilled organic sweet clover, by the different shapes. So we're going to do first a square, then a circle subset, and then a subset of the rectangles, changing the name each time, adding a .s, .c, and a .r, so that we have 3 different objects. I'm just going to highlight that. And you will note here that the rectangles returned nothing, 0 rows, and with no length. So why is that? Let's go back and look at the FE organic tilled sweet clover data, and I'm just going to highlight it and press Command Enter, and that will bring up just that data set. And if we slide back up here to the top of it, you will notice that we have plots that were circles, plots that were squares, but if we slide all the way down through, we had no rectangle plots. Someone didn't do their job and sample rectangles as well. So that'll come back in. So we can do the exact same thing for safflower when we think of it in this hierarchy. Well, again, now we're taking the safflower data. Note here SF for safflower, SF for safflower. So we're using the other data frame we subset, and we're just going to simply repeat those 3 subsets so that we have a square, circle, and rectangle. So now, for all of the organic tilled plots, we have a single data frame with a single data frame for each of the squares, circles, and rectangles. So now we can calculate the mean richness of those by using the mean richness data frame that was in there. So all the names were transferred over, and then we know them, and we want to calculate the means by area. So we're using this tapply, which stands for table apply. And this is our table, and we're going to apply based on the criteria that we calculate the mean for all unique values of area. So if I don't save that as an object and I just run it quickly, it will come out looking like that. So we have our point, our hundredth, tenth, quarter, half, 1, 5, and 10 meters squared. We have a richness value where we calculated the mean for those. So if I execute the command again with the blinking cursor on there, it'll execute the whole command line. Notice the difference here and here. So now we saved it as ot_sc.s.rich so that we know that it's organic tilled, it's sweet clover, it's square, and it's the richness. And then we just basically repeat that for each one of the shapes. So we do it for circles, and then we do it for rectangles. But if you remember, we had no rectangles, right? So if we go look at rectangle, did it return us an error? No, but it said it's logical that this is 0 because it didn't have length. So we want to do the exact same thing for safflower, right? We want a square, a circle, and a rectangle. We want a mean richness value for those by each one of the areas. So we'll just execute those commands. We got no errors. We can go back and look, and we can say that we know the object OT, organic tilled, SF, safflower, for the rectangle, and the richness was equal to these values right here. That notice the sizes across the top. So now what we'd like to do is actually plot those individual lines or individual species curves. And so we're going to skip this little bit right here, but I'll come back to it and I'll show you what it is right there. So the first thing to do is plot, and plot can have a number of different syntaxes. But here we're using plot where we give it an X and a Y. So X comes first, Y comes second. So we're using this names OTC rich because it's a nice convenient way to just get the unique values of the area. We can do that like that. They come up in parentheses now because they've been changed to reflect that they are that these were names. So we really would like them to be numeric, and I think that's not a problem using plot right here, but you can run into minor problems. So we have our X here and our Y here. We're telling it that we would like it to plot both types, and that is simply, if you have a question about that, go to your GUI, type ? plot, and it will bring up the help. The help will show that, oh, what does type mean? P means points, L means line, B for both, C for whatever, and on and on and on. And N all the way down for no plotting. So if you need help with plot, remember ? plot, and it's a large function and there'll be a lot of diverse help. Otherwise, Google it. So here we're plotting on the y-axis. We're telling the y-axis label is species richness. The x-axis label here is the frame size. And these are going to be all the tilled organics, but we're just plotting the circles first. We'll add the points and lines for the rest later. And then we're going to define the y limit here. That's what this means, that the y limit of the plot should be between 0 and 8. So the maximum is 8, the minimum is 0. Plot everything in between. So if we plot that, so Command Enter, it brings up our plot. You can see it puts our graph on there for us. And if you'll remember, the tilled organic sweet clover had recently been plowed, so there was not much in there for species richness. So now we'd like to add the other curves onto the data set, or onto this graphics window. And that's done here by adding the points to the plot. This time we're not calling plot again, we're calling points, and we're using the squares, and we're using the triangles for the next points. So what we did here was give it the OTCS richness vector. We told it again type 2. And here we're specifying the color and the symbol. So PCH stands for point character. COL is short for color. And color can be entered in many numbers of ways in R, from the RGBT coding to typing it out. Just Google it, but you can also color number 2. You can also highlight color number 2. So we're going to add this now by running the code. Apple Enter. Switch back over to our graphics window, and you see we added in the accumulation curve for organic tilled sweet clover when we sampled in squares. So I think we had no curve for the richness there, so we didn't actually need to include this line of code here at the bottom, but I just put it in there because we'll probably come back and use it again. So it'd be nice to take this graphic and add a little bit of a legend to our graphic, and I'm going to run the first legend here. We're going to put up circles are always going to be in black, squares are going to be in red, and rectangles are going to be bluish. So we'd like to keep adding the species accumulation curves for the organic safflower and the tilled organic, which was the other species that we sampled in. So we did that just like we did it before. We don't need to call plot again. We just need to specify that we want to plot the richness vector on the y-axis here, and again the area plot on the same axis there. We're going to add those points in for each one. So those are for the safflower, or the crop is in the field, there's more weeds. This time we used the same colors as we used previously here, but we changed line types. LTY stands for line types, and we changed that to type 2. I'm going to add another legend in here so we know exactly what that's going to look like. So safflower's dashed, or safflower's solid, and sweet clover's dashed. If I am correct, I believe there was also no circles sampled in the safflower, but I would like to go double check that. So here's what I'm going to do. I'm going to slide back up in my data set, and I am going to look at the organic tilled safflower right here, and let's see if we get anything. We'll switch back over, and it came up with logical equals 0, so obviously whoever was supposed to sample the circle plots in the organic tilled safflower did not get there. So that was a little problem in our homework. We're missing a couple of levels, but you can still answer the questions as best as possible. So that was the graphic window for the organic tilled plots. And you'll remember we also sampled in the organic grays, and we would like to compare those side by side. So basically, we're asking you to develop that code yourself. Here's the trick, and I put the note in here. Basically, if you just copy lines 45 to 88 up here, you can take that code and just substitute OT for OG, because here we're subsetting the grazed organic clover and the grazed organic safflower, but the only thing that's different is that we called it OG instead of OT. So when we go up here to OT, we just need to change this value. So you can really do that quite easy by copying, pasting, and I've already actually done it in preparation for the video homework. So I'm just going to sneak back into Box. Actually, I'll just go right here, and I'll just take the code for the missing years. Here we go. So here is the actual code. You guys can look at it as long as you can. I'll make the... So I did that, and I'm just going to do, it's the exact same thing. And here I'm just going to highlight all that data back down again, and then execute the command and go to my GUI window. And let's see, did that work? Uh-oh, I got a problem here. I did not find OGSF, OGSE. Oh, so I'm following my code back up. And it says there's an error in the subset, and that object FEOGSC was not found. So I need to, often you can accidentally forget to do that, and I think I forgot to execute these commands. So I'm going to execute those now. So now those objects should be found, and I'm going to switch back to my other script, the code for the missing stuff, and I'm going to just leave it all highlighted and execute the commands again. And this time we got no errors. I got that error because I had failed to save the needed data frames that were called in subset. So now I'll switch over to the graphic panel, and the graphic panel looks like this. So it looks like we did most everything. We have a dash and a solid line for each species, and we have all 3 colors represented twice. So the organic grays was better sampled. And so that's nice. And so I kind of want to make this comparison, and now I can save these 2 graphics. But I'm going to do this. I'm going to go back to my other data set. And you'll recall that I left up here some funky code that says this is for a Mac. So Quartz calls up the graphics device. So Quartz is the graphics device. And I want to have one that's 8 inches wide and 5 inches tall. But I don't, and now this extra line here is, I'm going to tell it this certain parameter. Par stands for parameter, and MF stands for a multi-figure graphic or graphic device. And it's MF row, so multi-figure, and I'm going to do it by rows. And I'm telling it here that I want to have 1 row, 2 columns. So now I'm going to execute that. And you'll see my graphics device popped up right there, which is nice. And now I'm going to go plot where we were in the non-added in code. And I'm going to highlight that down to here. And now I'm going to plot it. And I'm going to switch back over to my graphics device, have a look at it. So now we have the circle squares, and that's for the organic till. Looks quite nice. I'm satisfied. Now I'm going to switch scripts. And I'm going to go back to this code for the missing ones that you guys have to work out yourself. Remember, it's just switching O's and T's. And I'm going to just highlight all this and run that code, because I know there's only 1 plot in there. And I get this. So now I have the organic tilled graphic next to the organic grazed graphic. Looks nice. So now on a Mac, it's really nice. I'm just going to press Control S or Command S on that, and I can save that plot. And I'll just save that plot and drop it into the folder where I'm doing my homework. That's in here, and now I will name the plot. It's automatically saved as a PDF. It can be inserted into anything. I'll just call it species accum Fort Ellis, and now you can go get that and put it right into your homework. So now let's continue. If we go back and we look at the homework, so calculate and plot the species accumulation curves for organic grazed safflower, organic grazed clover, and all the different combinations for circle, squares, and frames. And then I'll leave that up to you to evaluate the mean difference in richness and come up with which size and shapes you would use. So now let's move on to sub-question B of question number 1. And that's fill in this table below with the means and the standard deviations. So I'm going to switch back. So here we'll have one look at what the table should be filled in. So we should have farming type, crop, frame, and the frame shape, and then the richness or the mean richness for all the different sizes. I'm going to switch back to my homework here, and we'll skip this. We repeated that, right? I put some notes in there to how to find it and substitute OT for OG. And you can calculate the mean richness. That's pretty straightforward. I guess I'll show you guys quickly that if you load library ggplot, remember you may have to install the package, but you can do this, essentially that graphic that I showed you there with much less code and much easier using this grammar of graphics plotting package, and it's just data FE, that the aesthetics Y should be richness, X area, that the group should be the shape, and the color should be the shape. I want to smooth those lines, and I would like this facet grid will grid it by the type, so the different types of fields. I'll execute that quickly, and it should come up nice and easy. Oh, yep, Did it do it? Let's close that. Oh, there we go. I got a little bit hidden back there. And you can take these out and you can manipulate the size and shapes. But you can see it's basically the same result as we got from the other curves where we have, and you can see we have a few problems in the data, like someone who did circle in the grazed organic clover maybe forgot to carry over the species they tested there, so they got very few, which is strange. Here we have our flat line. Here looks like we have maybe some problem in the data and the way the data was recorded and collated. So that would suggest we might want to go back and check it. But we'll just move on from there a little bit. So that's an example of using ggplot with much less code, and that's a pretty nice way to do it. And we'll come back to ggplot later in the semester. So here's one. So doing it, so you can answer question 1b by brute force, and that's basically going and calling up every single plot that we had, right? So we had, for example, we had organic tilled, if I remember the names correctly. So we had OT underscore S, so we can go say OT SC for sweet clover, and we had the squares, and we don't want it to be capital because R is very specific, and we could call it up. Oh, we didn't find it. What did I forget to add in there? OT, oh, I forgot to add richness at the end. That's what I forgot to add, dot rich. Now we can call it up and we can get those. So you can fill in the table very much brute force like that by going and calling up and looking at everyone. But there's also, tapply is much more powerful than that, and R is much more powerful than that. And one easy way to do it here is just to give it a list, where we use this tapply function again, and we want to know the mean of richness, right? Richness, mean. But here we're giving it a list of variables that we would like it to calculate the means for, or combinations of those means. And those are shape, area, treatment, and field. So if we just run that and switch back over, you can see, and you can mess around with the GUI windows and sizes. Oh, it's not going to make it all nice for us. Here, we'll try that again. There we go. I just reran the same line of code, and so now it's given it to us for, we'll start up where it was last called, right here. And so we have our grazed organic safflower, we have the size, and we have the richness that corresponds to it in the different shapes. That should allow you to easily fill out that table in question 1b. So I think that's pretty straightforward. So I also asked you in that table to give the standard deviations, and that's done really easily. All you have to do is switch mean and standard deviation here. Put SD is for standard deviation, and it will give you the standard deviations again for the same plots. Oh, but I realize I have them not. Need to do a quick fix here. This should be the same as this, so we need to add in, we've added in field, now we need to add in treatment, FE $ treatment. I almost forgot it. And we'll rerun that again, and then we get it in the same form as before. If there's no replication or there's less than 3 samples, you'll get NAs in there, or the data may be missing. Okay, let's move on to question number 2. It's really quite a similar question, in some ways much simpler in this context. So question 2 is, we'll switch over to it. Question number 2 is, calculate the mean number of species and standard deviation for each plot size and frame shape in the highlight data. So you'll have to fill in this table by yourselves. We're using the highlight nested data, but it's pretty straightforward. Remember, we just had 7 plots. You went to the plots, did a nested sampling, and then you record the frame sizes. So we'll switch back over to R here. And I'm going to switch over to my script. It always takes 2 strange clicks for some reason. But here we are. We're going to load in the highlight nested data just like we did before. I entered it, loaded it up. It looks fine, no major problems. I'll shrink down the size of these graphics the windows so you can see a little bit better. Stretch that out over the top. And you can mess with these any way you'd like to and arrange them. So first thing we're going to do is take a look at the data just like we did before. So we know that the data set is 119 rows by 53 columns. The names are this. There's 52 columns, each corresponding to the species. If you go to the first few names here, because I don't want to type out names, I'll say names. Because I don't want to see all the names, I'd just like to see the first few columns. I'll say names, HD for highlight data, and this time I'm going to put hard brackets around the end, and I'm going to say that I would like all the names 1 through 10, so only the first 10 names. And those are site, treatment, shape, recorders, size, and richness. We're just going to deal with that data for right now. So we're doing the same thing that we did in the first problem. We're just going to subset by circle, square, and rectangle. Execute those commands. Remember, HD, our highlight data, was the big data object, and we had the column shape, and we want, for the first one, for HDC, we want only the circles, equal to circle, and then square and rectangle. If you use one, we'll come back to that later in R, but one equal sign means it's actually equal to. Two equal signs is a logical evaluator. And we'll talk about some of that a bit later when we do some more complicated subsets and changing and manipulating of data. So we're going to use this tapply command again, and we're just going to calculate the size by mean, and we can see it popped up there. And we'll calculate that for the circles, the standard deviation for the circles, and then we'll do it for the other shapes. I put it in for the rectangles for you, and you'll have to manipulate the data for the squares. Fill in that table, you can and make sure that it's all correct, and you add the standard deviations. So now let's move on to question number 3. And that's just basically taking that same data for the different shapes, but this time we're only going to deal with the 1 meter squared size plots. So this time we're going to subset the highlight nested data, HD, by size, and this time we want the size to equal 1. And we're going to name that HD1, execute the command, and this time we want to just make a rough comparison using a box plot. So we'll bring up the box plot and call that nice box plot over here. Here's the answer to this question, more or less. I squished it in there. I'm going to get rid of it now. So there's lots of ways to manipulate graphics in R. Here's one a little bit fancier way where we added in a Y label, an X label, and a main title. That looks all right. But then we want to get even fancier sometimes, and I like to control the size of my graphics. For example, in many publications, you're restricted to having your graphs in one column of text. So that's about 3.5 inches by 3.5 inches. So I'm going to make a quartz device, and I'm going to tell it it's going to be 3.5 inches by 3.5 inches, and that's what it's going to look like. And then I want to change the margins of the graphic. I'm going to manipulate these parameters, graphic parameters again. And this time mar, I'm going to manipulate mar, the margins. And you can look under par to get this information. But basically there's a bottom, a left, a top, and a right. Those are the order. And so I'm going to set those I'm going to set the bottom and the left at 4.5 lines and the top and the right at 1.1 because I don't need so much space there. So I'm going to execute that command. And then I'm going to run this same box plot again, richness by shape. But this time I also manipulated the y-axis so that it'll appear as 1 raised to the second. And I also made the x-axis label slightly larger by saying CEX, which stands for character expansion, dot label, make it 1.2 times the normal default. I'm going to just highlight that. There we go. Ooh, so I lost my square off the end there, so I'm going to squeak it over there a little bit. So I maybe should have made that 4 by 4. So now we have species richness in 1 meter squared, and that we have it by circle, rectangle, and square. And I'll leave it up to you guys to interpret the results. So now let's move on to the R code for question 4. And the question 4 deals with the high modified Whitaker plot that we recorded in highlight. And this time we're using the highlight Whitaker data 2017. It's actually a .txt file and not a CSV file. And you'll remember we had 1 meter squared, 10 meter squared plots, 100 meter squared plots, and the big 1,000 meter squared plot that had everything. So let's plot the species accumulation curve for that, and then we'll talk about a little bit about the results. So I'll go back over here to the script. It always takes 2 clicks. Don't ask me why. So here's question number 4. So I'm going to load the highlight data, read .table, import the highlight data, no main problems up there. I'm going to look at the class of the area variable. And what's the area variable? We can go back and type in MW modified Whitaker $, area. And we can see we got our area. So the dimensions of our modified Whitaker are 15 by 65. And we have 1, 2, 3, on the initial, we have 10 1 meter plots, 2 2 meter plots, 100 meter plot, and we're only supposed to have 1,000 meter plot, but somehow in the data we ended up with 3 different counts of the 1,000 meter data. So that was a little screwy. We'd have to think about how we might want to deal with this if we were reporting or publishing this data. And in class, we won't worry about it too much. So let's go and call up the names of our data set. Again, we get this big long list that goes out to 65. I think I'll just call up the first 10 names. We'll do 1 through 10. And so we have recorders, frame size, area, plot, total cover, and the total vegetation cover. Bare ground, litter, rock, and we start to get into the others, but we have richness in there, number 9. So we want to be using this richness variable again, and we'll be using the area value. So first of all, we can just simply do, just like we have been, we're going to take the richness value, so modified Whitaker, $richness for just the richness column, and we want to calculate the mean based on the area. So all you have to do is apply that. So in all the 1 meter squared sizes, we got an average of 9.5 species, 20.5 species, and the 10, 30 in the 100, and 41 in the 1,000. So that's our species area curve, right? We could calculate a standard deviation for that. And we only had 100 meter squared plot like we were supposed to, and 3 ones for some reason. You can see it's pretty large standard deviation. So now let's just go plot. That's question 5 really. Let's plot that. So we're just going to use our area and our richness. Call up that graphic window, and you can see that's what our graphic window looks like, right? So for every plot that we have after we calculated, we use the richness vector and area, we have this line in here. You can see here's our 3 for 1,000, here's our 100 right here, and then the smaller ones are all located in here. So that's nice, we can see the raw data, but now we'd like to maybe put the mean line through that. And we're just going to calculate the mean richness for area here. We just did that above, and it's the same code on 167 as it is on 173. This time I'm just saving it as MRA for mean richness by area. So I'll just execute that command and save it. And now to this plot that I have still up there, I'm going to add in the curve. And so I give it points. I give it an X value, a Y value. This time I'm going to make the point character number 19, which I know is a closed filled circle. It's going to be blue. I'm going to type both types of lines, and LWD is line width. I'm going to increase the line width so I can see it because I'm getting old. There we go. So I put in that species accumulation curve. So now that we can see our species accumulation curve there, which is pretty good actually. So we do get quite a lot. I'll let you guys interpret that. So now there's better and more sophisticated ways to do species accumulation curves, and I'll show you guys that here. So the first thing we'll need to do is install the vegan package. So that would be either you can go to packages and data package installer, or you can type install.packages and put vegan in parentheses and in quotes, and it will install. But when you get to it, we're going to require vegan. But the first thing we'd like to do is know how well our small 1 meter squared plots, if we increased replication, would we get close to what we sampled in the overall 1,000 meter plot? And so I'm just going to subset out the small plots. You can do it in two ways. You could do it this way, where we say subset modified Whitaker by area, and we just want area equals 1. Or also we know that we can just go get that data. We can look at it real quick if we need to slide it up and inspect it. Oh, it's lots of species and columns. So really, we could take that out, or we could just take small 1 through 75, and this will be veg W. And we'll take that small data frame, and we'll get one, oh, I forgot to save it. We'll get small 1 through 7 through those. And we'll just pull them up so the data is up there. You guys can go look for it. We can type, easily switch back and type dim veg W, and we'll know that it's 10 for the 10 frames, and we have 56 columns. It's not necessarily so important, but we require V. So now let's take those 10 columns and let's use this require vegan, and we're going to use this function in vegan called species accum. And if you execute it, oh, I got to require vegan. It's going to load the packages, and then I'm going to execute space W and call up space W, and it gives us the sites 1 through 10. It gives us richness that gets all the way, and then what that standard deviation would be. So if you compare these values, let's go down here and we'll plot it. And there you can see that. And just for fun, we could actually add in oh, it's not going to be quite right. We'd like it to be 1 through 10. So we can see that actually if you use just the 1 meter squared plots and we get an error, that we get up close to over 30 species, which is interesting because that's about the same number that we calculated just by surveying the 1,000 meter plot. So what does that mean? I'll leave it for you guys to interpret. You can also do a nice box plotted version of that. And I recommend comparing this last box plot to the end of the species accumulation curve for 1,000 meters out here from the curves above. And that will help you on your interpretation. If you have any questions, please post them in the discussion on D2L. Thank you for listening. I hope this was helpful.